Hi everyone. The logo reminds me I forgot my umbrella. I left it in the office. It's like, so my hair's going to become really, really messy very, very quickly. All right, so thank you for coming along to the talk today. It's good to see that you all came back from the break rather than just staying there drinking coffee. This talk is called Building Cloud Native Applications with Go. And yes, I'm Mandy Waite. I work at Developer Relations at Google in London. And my Twitter handle is @TechGirl. You can also get me up on Google+. How many of you are still using Google+? Okay. Oh, what are you laughing for? I don't understand why people always laugh at that. So, anyway, so if you want to tweet me at any time, my Twitter handle is on the bottom of the slides. So please feel free to tweet me. I'll also be in the room downstairs for lunch. So if you have any questions, we're not doing questions this year for some reason. So you can come and find me later on today, and I'll do my best to answer for you. So we don't have much time. Half an hour is not a huge amount of time for a talk, maybe just the right amount. We're going to talk about this stuff on the agenda. I don't normally do agendas, so I'm going to skip over it very quickly. It's gone. That's out of the way now. So we're going to talk about cloud native. How many of you are familiar with the idea and concept of cloud native? Okay, not so many of you. Okay, let's talk about this then. So this all stems out of things that have happened with cloud computing. And when we talk about cloud computing, we don't necessarily mean Amazon AWS or Google Cloud or Azure or DigitalOcean. We talk about the idea of doing things in a different way, about building virtualized infrastructure, large lumps of infrastructure that can be virtualized and be provided to engineers to run applications on. And the first wave of this was colos. We got to a point when we were building systems where we had so many machines that we had to locate them somewhere else. So we located them in somebody else's data center, and we would pay them for that space. We would still own the machines. We would still manage the machines. Then we moved on to the second wave, where we took all of those physical devices and we virtualized them. We turned them into their virtualized equivalents. And we built virtualized data centers. We're still working with the fundamental same bits as we did before. We're still working with CPUs and processors, memory, storage, virtual machines. We're still working with all of those same things, but now we have abstractions and we can wire them together in interesting ways. Google used to do this up to 12 years ago, and we found at some point it just wasn't going to scale for us. So we had to do things differently. So we wanted to move away from this idea that we had to work with all of the old familiar concepts and do things very differently. So that kind of brought on this idea of the third wave of cloud, which is what we think is true on-demand cloud. And again, I don't mean this as Google Cloud Platform, I mean as a thing we built internally. So this is all predicated on the idea of automated services and scalable data. And ultimately, it allows us and allows anybody who uses this kind of methodology to invest energy in developing applications and not have to worry about managing infrastructure. You still have to manage it, somebody has to, but the developers don't need to worry about it. We abstract that out of the way. And with this rise of cloud computing has seen a requirement to think differently about how we build applications, and that is what cloud native is fundamentally. Moving away from these low-level things that we built systems with before, to different levels of abstraction. And Cloud Native provides that. And it provides it through things like containers for packaging and isolation, cluster abstractions. So now we take the idea of lots of machines, like say one of our data centers, and we pull them all together, and we have a pool of compute resources on which we can schedule work. And that's the next component, which is dynamically scheduling work. We don't want our engineers to have to worry about SFTP in a binary to a machine, SSHing into the machine and standing up that binary. Basically, they have a binary, they have some configuration, and they will send that to a scheduler that will schedule the work somewhere within the cluster. The next stage is microservices oriented, and all of these things, all of the things above this play into microservices. It's almost like microservices were developed specifically for cloud native. They weren't, but they play into it really well. So what we can do is we can decompose large monolithic applications, and we can run them on cluster abstractions, scheduling individual components dynamically, scaling them dynamically as well. So this plays very nicely into microservices. The next thing is deep visibility. For cloud native, one of the fundamental requirements is that you can monitor your application while it's running in a very deep and meaningful way. But also Cloud Native actually, because of the way it's architectured, actually provides the ability to do that as well. It's interesting that at Google, we have very high-level high-priority processes, things like Gmail and web search and YouTube. Then we had the low-priority batch jobs and map reducers, which generally run in a space that the others aren't using and get preempted when they're needed. But at the very top level, our highest priority jobs are things like monitoring. These monitor the running state of the system and make sure that it's working correctly. These are the highest priority jobs at Google. Cloud native is also enabled by technologies such as containers, including Docker and Rocket, and also by something called Kubernetes. Kubernetes isn't the only way to do this, but it's something I like talking about. It's my specialty, so I wanted to mention it in this talk. And Kubernetes provides many of the things that we see on the left here: the cluster abstraction, the scheduling, the microservices composition. So Kubernetes, how many of you have heard of Kubernetes? Hey, wow. Hey, how many of you are using it? Okay, more of you next time, right? More of you. I love Kubernetes. So, what's that? So Kubernetes, we're talking about it because it's written in Go. All of the applications we're going to talk about now are written in Go. 100% open source too. Extremely important. Kubernetes ultimately runs and manages containers. We look back on that previous slide, Cloud Native. It does much of what Cloud Native requires. And what we did when we built that third wave of cloud, we built a scheduler called Borg internally. We've had that for some time. Kubernetes is really inspired and informed by everything we've done when it comes to building that internal scheduler called Borg. And Kubernetes is almost like a fresh start. Borg is quite old. It's nuts and bolts. We bolted it together and extended it in many different ways. Kubernetes is almost like a fresh start. All these things we've learned are going back into Kubernetes and how it works. It's currently in the top 0.1% of projects on GitHub. And the fundamental idea with this, like Cloud Native in general, is to manage applications and not have to worry about infrastructure. Kubernetes, the architecture looks like this. I'm not going to spend much time on this slide. Was going to walk you through it, but this is the DevOps view of it. Let's not worry about that too much. What's the developer view of this system? It's something like this. Well, we have a control plane, in this case an API. We have developers developing applications, and then instructing the system via the API to say, please run this for me. And on the other side, we could have a data center, like one of our data centers here, or maybe a Raspberry Pi cluster. And we've had a lot of success building Raspberry Pi clusters. I wouldn't recommend this approach except for demos. I wouldn't run your stuff on this. Also, Google Cloud Platform. That's Google Cloud Platform's logo. And that's the only time I'm going to mention it. Amazon Web Services could be on the other side. It could also be on-premise machines. So ultimately, Cloud Native provides these abstractions that allow us to run stuff on all of these different infrastructure ideas. Okay, all right. With me so far. So, how are we doing? Oh, wow. I'm going quick. I'm going to sip water. I did timings this morning twice, and I was no way I was going to be that quick. I know I'm talking fast, but I've got a lot to get through. And if you don't understand any of it, please ask me questions afterwards. Or tweet me. Tweet me is always good. So, let's talk about deploying cloud-native applications and how we're changing that and how we're rethinking that. So the idea would be that we've done the first two stages for a long time now, ever since the advent of containers. So the idea, we take source code, we will build a binary, we'll lock down that binary version, and at some point we will package that binary as a container image. Most of you are going to be familiar with containers. And the container image pulls in dependencies in the form of libraries, things it actually needs to be able to run. Resources that need to be packaged up with the image, not need to be dynamically added at runtime. And also static configuration as well. So this is configuration that will be required wherever that container image is being used to run, not dynamic configuration that needs to be applied when we actually deploy something. So all of this stuff is packaged up into a container image. Then the next phase is to deploy stuff. And we're going to deploy stuff using different tooling. I've had to cut a couple of slides from the talk to make it a little bit more brief. But fundamentally, you could be using things like configuration tools, things like Chef and Puppet, Ansible, Vagrant. You could be using your own scripts. And there are other mechanisms as well that are coming to the fore, which is what we're going to talk about now. So let's first talk about the idea of immutability. I think immutability is a word. And it plays back into the idea of immutable infrastructure. Immutability gives us robustness. So ultimately, immutable components, they help with building robust deployments. So several things play into this. Containers are immutable, generally, not necessarily in practice, and if you use them incorrectly, they may not be as immutable as you'd like them to be. But mostly the attitude and the way you should think about containers is that they are immutable. That if you need to change one, you'll remove it and replace it with a different one. There are also various different immutable server images, and one we use as an example on the slides is Spinnaker from Netflix. But you can also bake your own immutable server images from which you can build machines. But then when we go beyond containers, I was originally talking about pods as well from Kubernetes. I'm not going to talk about that now. But when we have containers and we have images, the next step is to talk about deployments as being immutable graphs of immutable objects. So ideally, the structure of a multi-node deployment will be immutable as well. And then what we can do is we can construct an immutable graph of resources and then deploy that structure that we've created. So we have a new step in our process now. We've gone from build, package, deploy, and now there's a step in the middle called construct. So construction becomes a step in deployment. So what we need for this, to be able to construct a deployment, is some very simple declarative framework that we can use to construct them. So at this point, one thing we need to point out is you may often need to actually do some kind of runtime generation of configuration, a one-off process. And if you do need that kind of deep logic, you should use a first-class language, not a DSL. And if you do need to have code, it should be generating the immutable graph or the immutable configuration. We also would like to, not necessarily need to, support the idea of encapsulation and composition so that we can actually build up graphs of deployments from smaller, low-level intrinsics. So much like abstract data types or objects. But we still need deploy time configuration because ultimately we construct things up to a certain point, but at some point we have to deploy them. At that point we have to pull in configuration information, things like credentials and keys and passwords, and also environmental specific metadata, things that we're required to know at runtime. How do we discover other services and that kind of thing. And Kubernetes, we've talked about already, solved this via a couple of models. One is called the secret, and the other one is called a config map. And these are effectively volumes that are mounted onto the running containers. And the difference between the two of them is that the secret one only uses tempfs and never touches disk, while the config map is actually written onto physical disk. So we already have some of these mechanisms provided by Kubernetes to be able to allow us to do this. Then also the idea of construction with deploy time config. How does that actually work? We want to do construction, but we still want to be able to apply deploy time configuration. So this can be done by the mounted volume, which we talked about in the previous slide. So the volume itself can be part of a construction as well, and that structure will ultimately be immutable, but the contents may well, almost certainly, vary from deployment to deployment. So that also gives us a very powerful mechanism by which we can change configuration dynamically while we're running, as opposed to what would happen if we were using flags or environment variables. So now we can just go into the volume, we can change the data, and the mounted volume will provide that updated information to the running containers. We may need to restart and stop the containers still, depending on how it's configured. But ultimately, that configuration mechanism also is very powerful for when it comes to auditing of code and also auditing of config, and also managing configuration and source control. How are we doing? 15 minutes. Okay. So the flow of deployment becomes something like this, and I've got this expanded onto a bigger slide, onto another slide on the next one, so I can go into it in more detail. So we've gone back from the build package that we had before. We still have a deployment step. We've now added a construct step. And the construct step will ultimately be able to lock down the topology for us, compose things from other objects, and ultimately map everything out to physical resources. And when we do deployment, it becomes something like this. We now have the same configuration, but we've concretized it, and we've pulled in the configuration data. And that's mounted here on either running things that we call, well, these are the containers effectively, and here are the virtual machines. So we have the option to mount them on containers or to mount them onto the virtual machines directly. So one thing that really needs, or this kind of cries out for, is some kind of type system. So we want to be able to do construction by some type-driven configuration mechanism. So maybe we need a general resource called a type system. So this would come with a constructor for constructing a resource, which would take arguments and allow for parameterized creation of parts of the object graph. We want to be able to use a very minimalist DSL, not like the config languages today, config tools today, but very, very simple. Simple YAML, maybe with some parameterization too. And ultimately, this will provide all of the semantic meaning necessary to deployments. We can also encapsulate nested types, so this is very much object-oriented. We can also maintain a very close association with the types and the resources that they represent. We can also use real code, first-class languages for deeper logic. And ultimately, that will be run at construction time, not at deploy time. So we're actually building the object graph using this code. So let's talk about that type system and what that could look like. And this is kind of like, I had some real-life examples, but I decided to change them to make them more meaningful. So the idea would be we have a bunch of resources we want to be able to map out as types. And so we have a couple of them, or 3 of them, called out on the left-hand side here. The idea of a virtual machine and parameters. So we have a VM spec, and then the number of cores, the amount of RAM, the image that it's built from, the amount of memory. Okay, that's a mistake, sorry. But it could be other things as well, which is why the ellipses are there as well. Whatever needed to build a virtual machine or to create a template for a virtual machine. And then maybe we want to group virtual machines, identical virtual machines together. So we can create a VM group spec. And this time we say, this is the VM spec we're going to use for this group. And also we need a number of nodes for this group. The last one I'll put down here is cluster spec. So we may want to actually deploy this group of machines in a specific zone somewhere or into multiple zones. So we provide a VM group spec, and we also provide an array of zones to which to deploy it. And once we have this specification created, we can just make a very simple REST call to actually instantiate the entire object graph. So an example of this, we define, again, we're going back to YAML code. Sorry, it's not Go. We could use Go templates. So some of this does actually apply with Go templates. But in this case, we're using YAML. It's easier to read. So in this case, we define a front-end resource that contains things like a load balancer, autoscaler, network routing, and also some kind of managed instance group. We publish an image, and also we map in the zone we're going to use. We could actually make the zone a parameter for the actual template. So now we have a template for front ends. And we can create a template for backends as well. And then we can actually nest those deployments under a larger deployment. And we can do a large levels of nesting. So in this case, we have an application called MyApp, which has a front end and a back end. I've updated the wrong slides. There's a couple of typos on there. You'll probably spot them. But ultimately, the back end is much different resource from a front end one, but it does have a very specific configuration. So we can plug this into our nested deployment configuration structure, and then we can push that out to our architecture, our cloud-native architecture, to actually create the deployment. And that's what that looks like. So ultimately, at the end, we have the actual concretized version of this deployment with the runtime configuration or deploy time configuration plugged in. Okay, so construction and deployment. So that's how it effectively works. And that's how we're thinking about it and how we're thinking about building these kind of architectures. So we go from virtual machines to actual full multi-node deployments as resources, effectively. And there are some tools. We need tools to be able to do this. I mean, having the actual configuration files is one thing. Be able to generate those graphs is one thing. But you need some kind of tooling to be able to do it. And again, we're only talking about open source tools that are written in Go today. So this is Helm. And Helm has been around for a while. It works with Kubernetes. But it's always been not really part or a fundamental part of Kubernetes. It's been outside of it. It can invoke the Kubernetes API to deploy a configuration. But now we've taken something we have internally at Google called Cloud Deployment Manager. Externally, actually. It's an external product called Cloud Deployment Manager. Combine that with Helm, which is now called Helm C, and created Helm, which is now the OSS package manager for Kubernetes. And this is a GitHub project. You'll find it there. And it's still very much in progress currently. But that is entirely written in Go as well. So that works something like this. And we had this notion of chart files. The chart files are the configuration objects that we had before, that we talked about before. You'll use Helm to create the chart files, and then you'll package them up and store them into some kind of repository. Now, at the moment, this could be a storage bucket in S3 or in Google Cloud Storage or maybe some local repository. But ultimately, it cries out for having some kind of managed repository to hold this kind of configuration information. They're called chart files currently. The name isn't obvious to me. I think as open source projects go through multiple iterations, people come up with better names for these things. So ultimately, I think that name will probably change. So this is the client-side stuff. This is used to actually generate those configurations. But we also need to be able to deploy them as well. And this is where this part comes in. So this is Kubernetes here. We have an API and we have a pod. The pod is a grouping of containers, often just one container, a grouping of one, which is quite interesting. I did have a slide explaining what pods were. But basically, this is running in Kubernetes. So it's been deployed to Kubernetes, it's running there, and it will be able to provide all of our deployment tooling necessary to actually create those deployments. So what happens is that we, as a user, will develop the template, which will be used to provide configuration information back into the chart that we've already created. We'll pull down the chart, combine it with the template, and create a new dynamically generated chart, which will push out to this tiller component running in Kubernetes. That will be the install process, effectively installing the chart. That's communicated over gRPC and proto buffers. And then Tiller itself will say, OK, I have this thing. I need to actually make this a thing, make this a deployment. So it will render the deployment and then push it out to Kubernetes via the API. That will be done using REST and JSON, and it has the ability to do creation and updates of these running deployments. So that's how one way we can do it. There'll be other tools as well to be able to do these kind of things. And when we're looking away from Kubernetes, maybe with Docker Swarm and other examples like that, you'll be able to do very, very similar things. Again, it's all cloud native. I just want to kind of talk about some other tools as well that play nicely into this. And one of them is a distributed key value store called etcd. This is a fundamental component of Kubernetes. It was generated or created outside of Kubernetes, but nowadays Kubernetes uses it to store all of its cluster state and configuration. It implements the Raft protocol, consensus-based algorithm, and that is also 100% open source and written in Go. The next one is Prometheus, and Prometheus is a single system that can be used to monitor an entire stack. It was designed specifically for use with Kubernetes, and it's extremely powerful because of that. Again, it's also 100% open source and written in Go. I'm not going to go into any details. We'll share the slides afterwards. And I may actually share the bigger slide deck that I had this morning before I started removing things, including the slide with Docker on it. I had to drop the slide with Docker on it. But that wasn't through any kind of ill intent. I just didn't have time to talk about it. And you all know what Docker is, right? OK. So we talked about all of this stuff. We talked about cloud native. And I think you can see that Go is pretty much the programming language for this wave of computing that's driving forward, right? Cloud native is being built with Go. And I think that's extremely important. So one of the questions that kind of comes up, and the reason I wanted to do this talk in the first place was, why is that? What are the reasons for that? Many of you will probably have your own opinions about that, but I wanted to share with you what my opinions are. And I was thinking this morning that I didn't actually include synchronization in this list, which is interesting. But I actually thought, should I add it? And I decided not to, so I've left that off there. And you can maybe ask me later about why I did that. So why Golang? So I think one of the reasons that Go was originally created was precisely for this reason. We looked at the things that we had internally, the tools that we were using internally, the languages such as Java and Python, and none of them really fitted the bill for large-scale collaborative projects with distributed groups of engineers. Okay, so what we did was set out with Go to actually create something that did that for us. And so it has been designed from the ground up to support this very mechanism that's required at Google. And it plays very, very nicely into the idea of building these kind of systems, designing these kind of systems as OSS projects on GitHub. So I think that's really, really powerful. And I think that's why Docker did it, and that's why Kubernetes have done it, and that's why other people are doing it too. I also think extremely important, and I think Jerome at Docker has called this out as well a few times, static compilation is extremely important. Trying to distribute binaries when you have virtual machines and dynamic languages is very, very complex and often extremely unwieldy. I knew I was going to struggle with that word, right? Unwieldy. So static compilation is extremely important as well. I think another thing that plays into that is that for the first time, we really have a very strong alternative for building command line tools to C and C++. Traditionally, many, many command line tools have been built with C and C++. The ability to redistribute them very easily is extremely powerful. You can't really do that with a dynamic language or with a language running in a virtual machine. So Go, I think, has for the first time provided us with an alternative. And when you think of systems like Docker and Kubernetes, these things start with command line tools, right? User interfaces are an afterthought, effectively. So we need really functional and simple to use command line tools. And I think Go is the strong alternative for actually creating those tools to C++. Also, low-level primitives. I mean, some people would argue that Go is fundamentally a systems language. And the fact that it can support these low-level primitives, which are ideal for doing networking, for managing processes and PIDs, and making syscalls, makes it extremely suitable for this kind of architecture. And this is a highly scalable distributed architecture as well. So again, Go plays very, very nicely into that. And again, I think if I was going to put concurrency in here anywhere, it would be here. But instead I put critical mass. Because I think now, if you look at the projects on GitHub, there are very, very many projects on GitHub using Go. And I think when you look back at somebody like Docker who took a risk in using Go to build Docker, I think that risk is starting to go away. People already now see that Go is the right choice for building this kind of platform. They don't need to actually investigate it and much more than seeing all of the good things that have come out of it already. So I think the critical mass now makes it pretty much a no-brainer when you're starting out a project, a high-level project like Docker or Kubernetes, to choose Go as the language for building it with. So I think they're the reasons. So ultimately, what we've done, what we've talked about in this talk, and I've got like 2 minutes left, which is amazing. And I've probably spoken so fast you've not understood what I said, which is kind of worrying. But I feel pressure to get done in time. How do you deploy applications built for the cloud? So various different things play into this. I thought I had another slide. I changed this. Okay, right. Don't break production. Complex upgrades and sequence and reuse are important. And the kind of rules around that are construct, or what we've shown you, are construct, deploy graphs offline and then roll them out immutably. Use a real language only to generate declarative instructions and to mount volumes for secrets and runtime configuration. And finally, if you want to find out more, and I've kind of limited it to the 4 things we've talked about, Cloud Native, the Cloud Native Computing Foundation is at cncf.io. Our URL is really easy to remember nowadays. It's cncf.io, Prometheus.io, Kubernetes, really cool. So you can find out more about Cloud Native at cncf.io. All of the principles of Cloud Native computing are laid out there. If you want to find out more about Kubernetes, you can go to kubernetes.io. They all have GitHub projects, and they all have links to their GitHub projects on their front pages. If you want to find out more about Prometheus, prometheus.io, and Helm, helm.sh. They broke the rules for some reason. Helms, there must be a reason they did that, I'm not sure. And ultimately, this talk has been building cloud-native applications with Go. If you have any questions, please feel free to tweet me at TechGirl. Thank you very much for your time. Enjoy the rest of your day. Thank you.